Welcome to this presentation. My name is Mark Scythian. The date today is August 2nd, 2025. So in this presentation, we are going to inspect all electrical components across this DC series parallel electrical circuit using a multimeter. So we can start out by setting the multimeter to the ohms 20 range with the motor turned off. So the switch, while connected to the battery, has zero current, but exactly opposite to the voltage rating, so negative 12 volts. That's a good switch. So we know that we can't test the motor's resistance when the circuit is in the off or open position, so that's not even applicable. That would be no solution or infinity. So we turn it on. So if you're not sure what the procedure is, you can also use the Ohm's law equation to figure that out. So then if we actually have 12 volts and 431.7 amps going to the motor, and again, there may be a variation and there may not be a visual detection of performance of the motor, but you were just testing it as per inspection, you could simply just take a previous calculation before using the ohms meter of 12 volts E divided into 431.7 amps I, and then if your ohms meter reads out 0.028 plus or minus 5% error, then it's good. The battery, the electric motor's internal resistance, or the electric motor's dynamic resistance, and the switch are good. So next, we turn off the motor and we test the parallel resistor using the ohms meter, and then we also switch it over to the DC voltmeter, and let's say we test for both values. Then that means there is indeed a current drop of 1568.3 amps or 1570 amps going back to the source. Other alternatives is the built-in inline ammeter on the parallel circuit, which may be on some systems. So you can use the push to test function on that ammeter, and if it's validating 1570, then there's nothing to test. That's a good circuit. And if we're also using a watt meter, even though the criteria is only using the multimeter, but if you did have a watt meter, you could simply pre-calculate the 1568.3 amps I times 12 volts E and calculate 18,820 watts. So that should be about 18.8 kilowatts on your watt meter. If so, then the entire parallel circuit here is good. This then allows you to manually calculate the amperes on the circuit. So in this case, if we did that, we would get the 1568 value for the amps. And again, most multimeters are capped to 10 amps, so you couldn't use the multimeter to do this. And the other option is a dedicated ammeter, or just use the values of voltage and resistance that were recorded using the volt and ohm meters, and then manually calculate the current. So the same thing again, you could put your ohms meter here, positive, negative, where appropriate, and record the voltage drop across the series resistor, and then of course the constant resistance, because these are not adjustable resistors. So both constants, voltage and resistance, recorded, and then you know what the current should be because current remains constant in series. So when we turn on the circuit, we're discharging 2000 ohms on series, multiplying itself times 0.00175 ohms to then drop 3.5 volts away from the 15.5 volt battery, and then 12 volts remain to parallel, which then go to the motor. So validate that if you are in fact getting 3.5 volts and 0.00175 ohms across that resistor on series, you will calculate 2000 amps. So that is a good circuit. And again, the other options is the inline ammeter from the battery and then push the test. So the next inspection criteria is to test the battery's internal resistance with a load while it's turned on and without a load when it's turned off. So in order to figure out the battery internal resistance, you have to figure out the voltage draw away from the battery. So in this case, we are dropping 3.5 volts on series, and then we are sending 12 volts to the motor. So all voltage, all 15.5 volts are discharged. And then that's subtracted from the 15.5 volt rating, so that leaves a 0 volt internal voltage when the circuit is energized. And then we can simply divide the internal voltage into the effective current draw, because we're dealing with both series and parallel circuits. So what is relevant, whether the parallel circuit dissipates the current into heat or sends it back to the battery using a PWM, it's still effective current of 431.7 to the motor. So 0 divided to anything is 0, so it's approximately 0. There might be just a slight value, but it's theoretically 0. So what does this do, this test? This validates that there are no internal shorts in the battery. And then we do the same test, but with the circuit off, so then it becomes a no load battery internal value. So that's going to be a slightly higher standing value for battery internal resistance compared to the load energized state. So we could just use Ohm's law, and again, we do have 15.5 volts in the negative range when the circuit's energized, but it will behave when the voltmeter is placed across the battery when it's turned off as a absolute value. So depending on the multimeter, you'll either get the negative 15.5 or just its absolute value. And so then you calculate a slightly higher internal resistance of the battery. And this is not exactly the same as, let's say, a purely series circuit connected to the battery. And then the motor's dynamic resistance multiplies itself times whatever current's leaving the battery. This will then determine the voltage or load draw from the battery, which is then subtracted from its voltage rating, leaving then the internal voltage, which is then divided into the constant current, because it would be a purely series circuit. But in this case, we are accounting for everything basically taken out, everything put back in. And so it is a pretty straightforward calculation of a slightly higher battery internal resistance when off, and a much lower or almost 0 internal resistance of the battery when on. So that could actually be toggled in real time, and you could see the internal resistance change to approximately 0 to slightly above 0. So that also validates there is not only no battery internal shorts, but there's also no key off drains. So that all that's left is continuity testing elsewhere across circuit connections, contacts, wiring, and grounds or ground. So then the inspection is now complete. And if you did have a problem with the resistors, like say on parallel, you would have an insufficient current drop because the resistance would be too high if the resistance on parallel was shot, and then you'd have an overcurrent greater than 431.7 going to the motor, and then the motor's current limiter would prevent the motor from running due to overcurrent to protect the motor from burning out. And if you somehow had an under resistance value on parallel, then of course you would have insufficient current, so then the voltage regulator would shut down the motor for an under voltage condition. And then of course if you have a shot resistor at series, then you obviously would have more than likely too high a resistance, and then you would have too much voltage drop, and then there would be insufficient or zero voltage at parallel to go to the motor. That would shut the motor down. And then of course if it was an under resistance value at series, then you would have just the opposite. You would have an insufficient amount of current drop, and then you'd have an over voltage condition to the motor, and the voltage regulator would more than likely limit or shut down the motor from also burning out from over voltage. So again, the schematic, its planning can be tested for resistance and voltage and then applied into a current calculation. And so if those values, voltage and resistance, are not coming up properly, then you know it's either in the wiring, in the resistor, or in one of the grounds. So again, continuity testing will probably be the first appropriate step, and then start going into the voltage and resistance tests across the parallel and series resistors. But this is some guidelines to leave back. Thank you for watching this presentation, and have a great day.